Okay, so how many of you here have heard that the dinosaurs went extinct because of an asteroid impact? Everybody, just about. That's impressive, right? But this idea is really recent. And in fact, it happened not very far away from here. It happened just on the other side of the Gulf of Mexico, in the state of the Yucatan of Mexico. And it turns out the idea is only about 40 years old, which is kind of an amazing discovery. And in fact, the first time that we ever actually gathered rocks from offshore in the impact crater was only 3 years ago. And I'm here to tell you about that expedition and how on the IODP, Expedition 364, we drilled deep into the crater to bring back rocks to basically study how the crater was formed, what caused the mass extinction, and maybe gain some clues to how resilient life is or even how life started on Earth. So it's been a really fun voyage of discovery. So let's take it back to the origin of the idea. So this picture here is limestones from Gubbio, Italy. And the two people pictured are a father and son team, Walter Alvarez, who's a geologist, his father Louis Alvarez, who is a physicist. And the limestones on the bottom right are from the Cretaceous, the time of the dinosaurs. And on the top left are after the dinosaurs went extinct. And right in between was a half an inch, maybe a centimeter thick layer of clay. And so they were asking a simple question, or so they thought. What if we could measure how long it took for that 1 centimeter of clay to be deposited? Could we learn something about how quick the extinction happened? And so they measured it with what they thought would be constant, with their cosmogenic radiation coming from space, which creates elements like iridium and things like that in our soils. But it should be a really vanishingly small amount. And to their great surprise, instead of finding a tiny amount that they could come up with the length of time the centimeter took, instead they found an enriched layer, more than 80 times we would ever find on Earth. And they said, wow, there's only one way that's possible. We have to bring something from space that is constantly being bathed by cosmic radiation and crash it into the Earth, and then spread it all over the whole planet. And thus was born the idea that the end of the Cretaceous, the extinction of the dinosaurs and 75% of life on Earth, in fact, everything larger than about 60 pounds goes extinct, was actually caused by an extraterrestrial event, was caused by the impact of an asteroid. So in effect, everything you see on the left, the dinosaurs, which by the way, were feathered or bristled, they were not scaly, so those pictures are correct. The large marine reptiles you see, the ammonites that you see in the oceans, and even the kinds of plankton that lived in the surface of the ocean, all fundamentally changed on that day or that year. They all went extinct, like I said, 75% of life, but amongst the survivors were both some of the flying dinosaurs, they all became our birds, and mammals, which leads 66 million years later to a science party, and then we can go explore the crater. So that's pretty cool, right? So what did we actually learn about this event by looking at the geologic record, by looking at rocks around the world? Well, we learned that it changes depending on where you are on the planet. You see a layer that's only about this thick, that's enriched in those cosmic radiations, that's this layer of dust. Everywhere you see a yellow dot on that map. But as we move towards Texas, as we move towards the Gulf of Mexico, the layer gets thicker and thicker. And for instance, if we're off the East Coast, you'd see a layer about this big. And that layer actually shows below it plankton that existed at the time of the dinosaurs. After it, totally different plankton. In fact, only 4 species of all the plankton in the surface of the oceans made it through the extinction, and only 2 of those went on to become the progenitor species of all modern plankton. So it's a pretty big event for the oceans. But you also see glass spherules, these balls that exist within this layer that are actually made by a vapor plume coming out of the impact, condensing in the air and raining down all over the world, starting wildfires and so on, which leads us to even see ash and soot in the very top of this layer, along with that enrichment of cosmogenic particles like iridium. So it's a pretty amazing event, but that's off the East Coast. As we get even closer to the Yucatan Peninsula, it gets thicker and thicker and thicker, and obviously that takes us to where the crater is itself. Here is the state of the Yucatan and actually some of the surrounding states in Mexico, and buried underneath it is the Chicxulub impact crater. This is shown in gravity. We can see the edge of the inner ring of the crater. Those white dots are water-filled sinkholes that line the edge of the crater that some people like to dive in. And the ring in the center is pretty exciting. It turns out, and the University of Texas and my colleagues and I, we actually got to go image this using the same kind of techniques that sees into the subsurface like oil industry uses to look, only we were looking for science in this case. And the picture you see is actually a picture of the layers of rock down to about 10 kilometers into the subsurface that are actually collapsing down into the crater, and you can see that something is sort of collapsed over on top of them. And that something is kind of like a bump. And if you look in the top left, you see a crater from the lunar far side called Schrödinger, and a ring of mountains that surrounds the center of the crater. This is called a peak ring. It only exists in the largest craters in the world, and in the largest craters on the moon, and the largest craters on Mars, and so on. And we have it right there in the Yucatan Peninsula, buried beneath the limestones of Mexico. So our target, our excitement was, let's drill into it. Let's see what it's made of. Let's see if we can answer some fundamental questions about the event. So we went out on this platform you see. We actually got put up on it by that little basket carried by a crane. It's known as a widowmaker, so that was pretty exciting. Our labs were in shipping containers put on this thing, so really luxurious conditions, as you can imagine. And we pulled up rocks for 2 months that were directly from the time of the dinosaurs, or right after the time of the dinosaurs, and into the recovery of life from the extinction event. And we've studied those for the last 3 years, and I want to show you just 3 big results that we're excited about. First of all, these are the rocks, and what you can see is the white rocks, or the limestones afterwards. Those brown rocks below it on the left, that's the rocks that were from the recovery of life, those first few years after the Cretaceous ended. But then we see these crazy rocks that look like a fake countertop, right? Those are actually broken and fractured and melted rocks from the impact itself, and we have about 400 feet of them. Not just this much, not just a centimeter, but 400 feet, 130 meters of these impact-created rocks. Below that, we see rocks that were physically melted by the impact, by the pressure alone. That's those black rocks. And below that, we found hundreds of meters, thousands of feet of crushed granite that was actually brought from about 6 or 7 miles below the surface of the Earth and brought up into the surface of the planet at the time, and has now been buried. And even found evidence of a shock wave passing through the rocks. That thing on the bottom right is actually literally a shatter cone caused by the energy of the force moving through the planet. So this is all just in this one drill core, which is pretty amazing. And what did we learn? Well, first of all, we learned that impacts hit so hard, they cause the surface of planets to temporarily act like a liquid, splashing upwards, collapsing downwards, collapsing outwards, and so peak rings are in fact made of material that came from miles down, brought up, collapsed outward, and make a mountain, all within a few minutes, which is phenomenal, right? If we go to other planets and we want to see rocks from deep, the best place to go would be to go to impact craters with a peak ring and go sample those rocks, because they're not from the surface, they're from beneath. So that's a pretty cool result. We also think we have learned something about the way the extinction happened. Remember, the extinction was global, not just the bad day in the Gulf of Mexico, but everywhere. This video is from Europe. This simulation would be from Europe, and that's where ejecta from the crater is traveling through the atmosphere over the top of all over the planet. The bigger particles, like the yellow dots, are raining down through the atmosphere, setting wildfires, but the little fine particles are actually hanging out there for years and years and years. And the 2 things on the bottom right are a global climate simulation, like we study modern-day climate change. The red panel is what it looked like before the asteroid impact happened. The average temperature on the planet was about Texas in the summer. And after this stuff ended up in the atmosphere, these sulfate aerosols, we dropped to temperatures where the average temperature on the planet was near freezing, and much of the planet was below freezing year-round for maybe 15 years. And we think that's one of the major causes of the extinction event. We also learned, quite excitingly, that life finds a way. So looking right in the crater itself, looking at those first few years of sediments that accumulated right after the event, we actually found little tiny plankton that came back and occupied the oceans at ground zero. And even more exciting, those whole circles on the left of there are actually burrows made by organisms burrowing into the seafloor within a few years of the impact. In other words, life can find a way even at the greatest of stresses. And then lastly, our perhaps most interesting thing looking forward and backwards is we found all this evidence of hydrothermal systems, of hot spring-like materials moving through those broken rocks, but also moving through fractures in the uplifted granite. And in those, we found DNA from modern-day organisms that stemmed from these heat-loving types of microbial life. So we think these are clues to the way life gets going, potentially in hot springs or mid-ocean ridges or impact craters. And this might be the kind of places we should look for, places like Mars, to maybe find clues to how life gets going on other planets as well. So I'd just like to leave you with a couple of things here, which is to say that science requires bold ideas, right? Such as an impact crater could cause extinction across the planet. Ideas have to be molded by evidence, right? And the Chicxulub event tells us something about the vulnerability, but also the resilience of life on our planet, and that we should also always accept there are other ideas out there. Thank you for your attention.